Hold 4 marbles in your fist. Throw them onto a kitchen floor. Before they stop rolling, particle physics claims it can tell you almost exactly where each one should go. Left, right, fast, slow. That is the kind of prediction the universe lets us make every day. Now shrink the marbles until they are smaller than atoms. Make them live less than a blink. Repeat the test millions of times inside a machine buried 100 meters under the French-Swiss border. For more than a decade, one pattern has refused to land where the rulebook says it should. In 2013, the LHCb experiment at CERN reported a 3.7 sigma mismatch in a rare particle decay. In 2025, with a far larger and more sophisticated analysis, the overall tension still sat around 4 sigma. Physics demands 5 sigma before it calls something a discovery. So the crack is not wide enough to walk through, but it is still there. And that matters, because the rulebook being tested is the standard model, the best instruction manual we have for the particles that make ordinary matter. We built a 27-kilometer ring to test that manual. The universe answered with a smudge in the margin. Conveniently, the obvious explanation is that we measured badly. Except we measured again and again. The real question is not why one number is strange. It is why the strange number keeps surviving. The particle at the center of this story is a B Meson. Think of it as a tiny, unstable package of quarks that appears for an absurdly short time and falls apart. One rare decay produces lighter pieces plus 2 muons, heavy cousins of electrons that do not stick around. This decay is useful for a sneaky reason. According to the standard model, the B0 reaches those final pieces through quantum detours, temporary steps we cannot see directly, but whose effects can change the result. Imagine sending a ball through a sealed pinball machine. You cannot see the bumpers inside, but if the ball keeps coming out at the wrong angle, you know something inside may not match your diagram. That is what LHCb measures, the angles. The kaon goes one way, the pion another. The muons leave in their own directions. Physicists compress the pattern into numbers. One is called P5'. It sounds like a robot password. It is just a score describing the geometry of the decay. In the early data, P5' landed far enough from one standard model prediction to attract attention. 3.7 sigma in one region. Sigma is a way of asking how hard random statistical noise would have to work to fake this. 1 sigma, nobody loses sleep. 3, interesting. 5. Now physicists start using the word discovery. 5 sigma corresponds to odds of a random fluctuation of roughly 1 in several million under the assumptions of the test. History has trained particle physics to be cautious. A weird bump can disappear with more data. A suspicious result can vanish when a background is understood better. Science calls this discipline. Reality probably calls it quality control. And here is the annoying part. The P5' tension did not simply vanish. LHCb checked larger samples. The details moved. Local significance changed. Theoretical calculations improved. Some other famous flavor anomalies weakened or disappeared. But this angular pattern remained interesting. In 2025, LHCb combined measured angular information from 8.4 inverse femtobarns of collision data collected in 2011-2012, and from 2016 through 2018. The global fit still showed about a 4 sigma tension with standard model predictions. Not 5. Not a discovery. 4. Close enough to be irritating. Far enough away to forbid celebration. For something that might be nothing, it has remarkable stamina. Now we reach the part that makes this more than a statistical ghost story. The standard model is outrageously successful. It predicts particle behavior with a precision that makes most human engineering look like measuring a room with a banana. But it is not complete. It does not include a quantum theory of gravity. It does not explain dark matter. Physicists already know the instruction manual has missing pages. The question is whether this B Meson pattern is ink leaking through from one of them. There are 2 honest possibilities. First, new physics. An undiscovered particle or interaction could briefly affect the decay without ever appearing directly in the detector, like a hand behind a curtain nudging the pinball before it comes out. Theorists talk about candidates with names like Z-prime bosons or leptoquarks, heavy messengers that would let quarks and leptons talk in ways the current rulebook forbids. Second, the standard model calculation is harder than we think. Quarks do not travel alone. They are wrapped in the strong nuclear force, a storm of interactions that can imitate the kind of shift researchers are hunting. If those effects are not calculated perfectly, the crack may be in our mathematics, not in nature. That distinction is brutal. Imagine a safe whose dial stops 4 numbers away from where your blueprint predicts. Maybe someone changed the lock. Maybe your blueprint is wrong. Until you know which, you do not get to announce a new safe. And physics has another problem. The threshold is unforgiving. The last step from 4 sigma to 5 sounds small. It is not. You cannot negotiate with statistics or round up because the result has good cinematic lighting. Human beings are excellent at seeing patterns, useful with danger in the grass, less useful when particle collisions tempt you to fall in love with a fluctuation. So CERN does the opposite. More data, better detectors, better calculations. Try to kill the anomaly. That is the test. If it dies, we learn where we fooled ourselves. If it survives, the problem gets much bigger. Because then the most successful particle theory ever built may be describing reality almost perfectly, and still missing a rule. Almost perfectly is a dangerous phrase. A bridge that is almost perfectly calculated can still fall. A spacecraft that is almost perfectly aimed can still miss its target. And a theory that is almost complete can still hide a law we have never seen. For a universe with no obligation to be understandable, its errors are strangely specific. So, what would happen if we could finally identify what is causing this one? First, forget the easy science fiction answer. No responsible physicist can tell you this anomaly will give us warp drives, limitless energy, or another dimension. We do not even know whether it is new physics. Anyone selling applications now has skipped several chapters and gone straight to the merchandise table. What scientists can do is build a better test. CERN is doing exactly that. In June 2026, the LHC ended physics collisions for Run 3 and entered a major shutdown and upgrade program. More than a kilometer of the collider is being replaced as CERN prepares the High-Luminosity LHC. The goal is not to make particles more dramatic, it is to make far more collisions. CERN lists the LHC's original construction costs on the order of several billion Swiss francs. Apparently, even a machine that expensive can buy you a better question instead of an answer. The upgraded machine is designed to deliver about 5 times more collisions to the experiments. More collisions mean more rare decays. More rare decays mean smaller statistical fog. It is the scientific version of turning on brighter lights in a room where you thought you saw something move. The upgraded LHC is expected to return around 2030. Meanwhile, the old data are not dead. LHCb's 2025 angular result used runs 1 and 2. Newer Run 3 data can now be analyzed while the machine is quiet. The machine is quiet, the argument is not. And that may be the most beautiful humiliation in this story. We built the most powerful particle collider on Earth, collected mountains of data, and our reward is a 4 sigma question mark. Nature still refuses to provide the answer key. Elsewhere, Bell 2 in Tsukuba, Japan, hunts related fingerprints from a completely different collision style. Decade-spanning campaigns, billion-scale budgets, all aimed at catching a process that has been running correctly, continuously, without a grant proposal. Since long before anyone poured concrete under Geneva, we are spending fortunes just to catch up to a decay that never once asked permission to begin. So return to those 4 marbles on the floor. The standard model tells us where they should roll. Most of the time, it is astonishingly right. Then one rare decay appears. Its pieces leave at slightly wrong angles. We repeat the analysis. The tension changes shape, but it does not politely disappear. In 2013, one local P5' measurement sat 3.7 sigma from a standard model prediction. In 2025, the most sophisticated LHCb analysis of this decay reported about a 4 sigma global tension. 5 sigma is the line. We are not there. That is exactly why this is interesting. A discovery would give us an answer. 4 sigma gives us a choice between uncomfortable possibilities. Either a tiny, persistent mismatch is showing us physics beyond the standard model, Or the standard model is so difficult to calculate in this corner that our own best mathematics can imitate new physics for more than a decade. Neither option is boring, and neither lets us pretend the case is closed. The universe is not obligated to match our equations. Our equations are obligated to match the universe. So if this crack finally disappears, we will have learned how astonishingly subtle the known rules can be. If it survives the next generation of data, we may have found the edge of those rules. And then the question becomes larger than CERN. How can a universe run on laws precise enough to build atoms, stars, chemistry, and minds capable of measuring a 4 sigma deviation, while still hiding deeper layers beneath that precision? We can name the particles, measure the angles, and build a 27-kilometer machine to challenge a decimal place. But naming the precision is not the same as explaining it. So if the deeper rules of reality really are this exact, this layered, and this stubbornly coherent, who calibrated the system if no one calibrated it?